Okay, I'd like to get started. My name is Matt Glazer, and I'm chairing this second Materials and Photonics tutorial session. And our first speaker today is Dufresne from Yale University, and he's going to be telling us about optical manipulation and basic principles of optical interactions and how they're applied.
Super, thank you very much. It's always a great pleasure to be here in Boulder. And today I'm going to try to give you a mixture of a tutorial to introduce you to a field that you may or may not have heard about before, as well as tell you a little bit about the research that we've done in my laboratory. I'm not going to get, I'm going to go deeper on technique than I am on science, though I'm going to try to keep my discussion about technique at a scientific level about the ideas driving the technique, not sort of the details of apparatuses and stuff. Anyway, so I figured the core thing I want to talk about today is our optical tweezers. And the best thing to introduce you to optical tweezers is a movie that I wish I could say that I made. This is a movie that came out of Steve Quake's lab about 5 years ago. And in this movie, you see a guy named Robert tying a seven-handed knot in a single strand of DNA. Okay, this is an absolutely spectacular experiment. The thought of being able to manipulate a single molecule with this tremendous level of control would be completely unconceivable. I would say maybe even 20 years ago, even when the technology itself first came out. So let me just point out a couple of features in this movie. This long strand here is a 100 micron or so strand of DNA that has been decorated with a fluorophore. And one end of the DNA, both ends of the DNA have micron-sized polymer spheres attached to them. One of them was just left floating freely in the solution, where the other one was being manipulated not with a normal mechanical sort of manipulator, but it was being manipulated by a focused beam of light. Okay, and in the first part of my talk, I want to give you a basic idea of how this works, and then later I'm going to give you an idea for how you, applications. But the applications are not dollar sign applications, they're light bulb applications, and that they're scientific applications. Specifically, I'm going to talk about how you can use optical tweezers to do quantitative measurements of forces. Okay, so this thing, which was allowing us to tie a dot in DNA, is a very, very simple thing. It's simply a laser focused down with very high quality optics to a perfect spot, a diffraction limited spot. And it doesn't take much laser light at all to trap a micron-sized object with a high index of refraction. You can, in fact, do it with a laser pointer. And in fact, in my laboratory and in many other laboratories, people have just stuck a laser pointer through an objective lens and trapped particles. It's a very easy thing. The laser's the cheap part. The lens is the expensive part. Anyway, so typically with this simple device, you can trap dielectric objects with a size between about 100 nanometers and 100 microns or so, with tricks to extend it on either side. How does this work? How can you possibly be able to apply forces and manipulate things without actually touching them? I will explain how that works in a second, or now. So if you look at the focus of this laser beam, the light is very bright, okay? It's about, I can't remember if it's 1 million or 1 billion times brighter than the flux from the sun on the surface of the Earth, but in any event, it's awfully bright. And there are two basically types of forces that matter fields in this very intense radiation. One of them helps and one of them hurts, okay? And we're going to be optimistic today. I'm not going to really tell you much about the thing that hurts. The thing that hurts is radiation pressure. The basic thing of radiation pressure is that light carries momentum. And if my laser is moving from the bottom to the top, and I have objects which scatter that light, they tend to pick up some momentum and move in the direction that the laser was propagating. That doesn't really help you trap. The thing that allows optical trapping to work is something called the gradient force. And I'll explain how that works in more detail. But the basic idea, it's a force that brings dielectric objects to the spot in space which has the highest light intensity. Okay, so the basic physics is very simple. Okay, the key point here is that dielectric objects are attracted to high intensities, high light intensities. There's two pieces of basic physics you need to know to understand that. The first thing is that an electric dipole feels a force in a field gradient. An electric dipole doesn't feel a force in a constant electric field because the positive charge and the negative charge get pulled with equal and opposite forces in opposite directions, and there's no net force. But if the electric field is a little bit stronger on one side than on the other side, there's a net force that pulls the dipole basically towards the larger electric field. Mathematically, you can express that as a combination of a gradient operator and a dipole moment acting on the electric field. Okay, but a lot of objects don't have permanent dipole moments, but most matter can have induced dipole moments, so that if you put a neutral object in an electric field, the electrons get pulled one way, the nuclei get pulled the other way, to make it really simple, and there tends to be a separation of charge in the material that creates an induced dipole moment. So if you take, and there if we make the simplest possible assumption, that the induced dipole moment is proportional to the electric field, we can substitute this in back to this equation, use Maxwell's equations and some vector identities, and you get a very simple result, that there's a force which is proportional to the gradient of the square of the electric field. And since light is a electromagnetic phenomenon, and most of you know that the intensity of the light is simply the square of the electric field. So there's a force that's proportional to the gradient of the intensity. So the gradient, of course, is pointing to the place where the intensity is the highest, so things are pulled to the focus of the laser beam. Okay? So that's the key physical idea behind everything that I want to tell you about. And we call that a gradient force. So I'm going to show you a little bit of data to give you a sense of the force scales and the length scales that are involved in this type of phenomenon. So I'm going to show you some, this is some data that a graduate student in my lab took, some very simple data. All it really is it's just the force that a micron-sized dielectric object, in this case it's a 2-micron diameter silica sphere in water. This object is freely diffusing near a focused laser beam with 100 milliwatts of power, and it's a 532 nanometer laser. Okay? So 0 is the focus of the laser beam, and you can see that to the left of 0, if you're pretty close to the focus, there's a large force pushing you to the right towards 0, and to the right of the focus, there's a force pushing you to the left. So it's creating a restoring force which draws objects towards the focus. Okay, and this data was taken by applying a known force to a particle near in a trap and looking at how the particle displaces in the trap. The details aren't important here. The key thing here is the magnitude and the shape of the forces. So you can see here that we have forces that are sort of tens of piconewtons in scale, and I'll calibrate that for you in a second. But also you can see the profile of this force is very well approximated by the gradient of a Gaussian. And when you focus, for those of you that know optics well, when you focus a laser beam, it makes a Gaussian spot. So using this, like I said, the force really does appear just to be the gradient of the intensity. All right, so let's calibrate this force scale for you. This force, about 5 piconewtons, turns out to be the amount of force that a single molecular motor inside of your body can generate. So there's this molecule called myosin. Myosin is a little motor, you can think of it like a train, that likes to crawl around a track. That track is called actin. And the way I move my arm like this, up and down, is by having a whole bunch of myosin crawling up and down the track of actin in my arm. A single myosin motor exerts, if this is a single molecule consuming ATP, exerts about 5 piconewtons of force. Okay, I can lift newtons of force, right? So that tells you, I'm a physicist who's interested in biology, so I find it absolutely spectacular that my biological control system with very rapid, tight feedback loop can tell 1 trillion of these guys simultaneously to work to lift up my arm. Anyway, that's a little bit of biology. But we're talking about piconewton forces. And this example already highlights one of the areas where optical tweezers are very valuable, and that's understanding the mechanics of these molecular motors. All right, so some people like to think of forces. I often like to think about energy scales. So if I take this experimentally measured force profile and integrate it, I get a potential well. So if you see a particle, this is once again a micron-sized dielectric object sitting in a 100 milliwatt laser beam. This is what the trap potential looks like. Okay, it's really deep. How deep is it? It's 3,000 kT. Some of you grew up in atomic physics, it's about 10 Rydbergs. Okay, so it's sort of covalent bond level binding between the particle and the focused laser beam. And the really important thing is if you sort of go like this and look at this shape, it looks an awful lot like a parabola. Of course, everything looks like the parabola near a minimum, but that parabolic approximation works very well in most cases. So we can model the potential near the bottom of an optical trap as a harmonic oscillator with the characteristic stiffness K, which people call stiffness. And if you want to use optical tweezers in the experiment, the values of K that you can attain in a real experiment are incredibly important to you. So this is a typical stiffness that you would see for a micron-sized object being manipulated by a laser. You typically get about a piconewton per micron per milliwatt of light. Okay, that's a good. That helps put the scale here if you want to do a real application. Okay, so here are a couple of real applications which I'm going to use to motivate some technical details, and then we'll go back to some physics. So the first motivation is very closely related to the movie that I started this whole thing off with. I showed you 2 strands of DNA that you could see that was being manipulated with 2 optical traps. Here actually I'm showing, this is from Steve Block's lab at Stanford. Here I'm showing 2 particles with a single strand of RNA between them. Here they're not fluorescently labeled, so you can't see the RNA, but you can see the RNA mechanically. You can see it mechanically because here we have 2 optical traps, and what they did in Steve Block's lab is they moved one of these traps to the left. And you can see at first, as I move this trap on the left to the left, nothing happens to the particle on the right. But after a certain distance, this guy starts to get displaced. Okay? So you can see that there's a mechanical connection between the left and the right particles. That mechanical connection is being made by a single molecule of RNA. And so if you know what your spring constant is, and you can measure all those displacements with high fidelity, then you can measure what people would call a force extension curve of a single molecule. So you can find out how much a molecule likes to be stretched or unstretched. All right, people have used these sorts of experiments extensively in the last 10 or 15 years to understand how DNA is transcribed by RNA polymerase, how viruses cram DNA into themselves, and a whole bunch of other things in single molecule biophysics, as it's called. But to do these experiments, you need some pretty sophisticated control mechanisms. You need a pretty sophisticated experiment. And so I want to spend a couple of slides. If you're someone who's thinking about using optical tweezers, you need to know like the different types of strategies that people use to control optical micromanipulation systems. And there are a bunch of different choices. The simplest thing you can do is, like I said, you just take a single laser and you focus it with a microscope objective. And when you have that sort of setup, you usually use some mirrors and some lenses, and you get inside of the microscope, And if you want to move things around, you usually tilt the mirror by hand, and you can move particles and beams of light around. That's great for many applications. It's especially good for undergraduate teaching labs, and lots of universities have this sort of setup in an undergraduate teaching lab nowadays. The most popular optical trapping setup today is based on time sharing, and that if you want to make multiple traps, you take a single laser beam and you have it sit in one spot, and then hop over to another spot very quickly. So if that switching back and forth is faster than the particle's native dynamics, then it sees a time average. And those of you that went to the laser show today saw exactly how this works, right? They basically had an optical trapping setup, and that they had some sort of acousto-optic device that was very rapidly moving the beam of light around so that faster than your eye could resolve, and so it would make all these patterns. You can do the same thing. You can do the same thing. HP health check. No, I do not want to do that. All right. Okay, great. So, yeah, for this sort of manipulation, you can really only make multiple traps in a single plane. An alternate trick, and this is the trick I'll tell you a little bit more about. It's the one of the trick. That's a trick. I was one of the people that helped develop this trick, so I especially like it. Is a trick where we use phase optics, often a liquid crystal device, to modulate the phase profile of a single laser beam to create multiple optical traps that don't necessarily have to be in the same focal plane. And also, you can do things that you could never do with time sharing, that you can convert Gaussian modes into Gaussian error modes, and you can do certain types of aberration correction like we heard about in the morning today. Tomorrow, Kishin Dulaki, I'm sure, will tell you about converting Gaussian modes into Gaussian error modes. Anyway, so that's sort of a high-level thing. I'm going to tell you a little bit more about holographic tweezers. The basic idea in holographic tweezers is that a single beam going through a lens makes a single trap. So all you need is, if you want to make a bunch of traps, is to put a bunch of lasers through your microscope objective. Okay? So, but the interesting thing about this is that the microscope objective doesn't care at all what you have in your optical table. All your microscope objective cares about is what the electric field or the wavefront is at the entrance pupil of the lens. So what we do is we calculate in the computer what the wavefront would be if there were a bunch of lasers passing through a microscope. And then we create some sort of phase object which emulates that interference pattern to trick a single laser into thinking that it's lots of lasers. Okay? So here's one of our early examples. We wanted to make a pattern of 19 traps on a triangular grid. We calculated what the interference pattern was, and the computer optimized it a little bit because we only wanted to manipulate phase, not amplitude. We made this mask in the clean room in silica. It took about 2 weeks from the beginning to end to make this device. We stuck in our optical train and we were able to trap lots of objects. All right. So if this is how if it worked for liquid crystal people, this is how we would be making holographic optical tweezers today, which probably means that no one would be using the holographic optical tweezers. But shortly after David Greer and I developed this, liquid crystal spatial light modulators became relatively inexpensive. And so instead of having a refresh rate of once every 2 weeks, you could easily realize refresh rates at video rate. And so you can make great, speaking of self-promoting and being young faculty, being sophisticated about trying to get money, a really good movie that involves, the logo of your university is always a good idea. So the first thing I did when I started my lab at Yale was to make this cheesy movie where I move a bunch of particles around and make a Y for Yale. And Lux, for 2 reasons. Lux is the first word in Yale's motto, and also we're using light. Lux is the Latin word for light to move these particles around. So this is a real-time movie. It's not sped up. We're moving 25 particles with a single beam of light. This is what particles do when you're not manipulating with optical traps. And this is what they do when you do. But like I mentioned, with holographic traps, When we calculate our interference pattern at the entry people of our microscope, it doesn't have to just be a bunch of collimated beams. They could be beams that are diverging or converging, and those converging or diverging beams will focus outside of the focal plane. And so we can also manipulate objects in 3D. The lighting isn't very good in this room, I think, or my contrast isn't so great, but when all the particles are the same color, they're on the same z-plane. The ones that are lighter are farther away from the microscope objective, the ones that are darker are closer. So here you can see that we're rotating these 5 objects in 3D simultaneously, in both the azimuthal and the polar direction. Great. So the point is that if you want to move lots of objects around at the microscale, the technology exists. All right. Pretty good. I'm going to skip past this slide because it's a little too technical, but I'm going to show this one. The point is that if you have lots of optical traps, you need a way of controlling them. And if you have just one trap or two, if you have one trap, you can use a joystick. If you have 2 traps, you could still probably use a joystick. If you're a drummer and you're outside life, you could do 4, but more than that, forget about it. So we've invested a lot of time in our lab to be able to develop closed-loop systems where a microscope and a computer can look at a sample, find objects, and then put them where you want in a predetermined pattern with no user intervention. And that's what I'm going to show here. What we do is we tell the computer, please find 25 particles. Trap them. It just traps 25 particles in the middle. And please put those 25 particles in a 5x5 grid. And it does. Now this is a pretty old movie. It's a few years old now. Things happen faster now, and also we have better error correction, so we can build things without defects. But the basic idea is that we can build complex adaptive matter, not from self-assembly, but from the top down at the microscale, and really intervene in complicated ways. And that is useful for doing all sorts of physics and biology experiments, as I'm going to explain in the rest of the talk. Right, so that was sort of the basic technology section. That's part of the talk. It's the foundation, the experimental foundation for how we're going to do experiments. And so this talk, I'm focusing on using these optical traps to measure forces. Okay, so piconewton forces are, for me, large forces. Okay, and those are the types of, in my laboratory, we measure piconewton forces to study cell biology. I'll also tell you later in the talk about measuring femtonewton forces, 10 to the minus 15 newtons. So it's a force scale that's important for colloidal physics. All right, so let me give you a little bit of context about the scientific problem that we're working on. One of the biggest problems in biology is how we think, okay? And one very simple aspect of how we think is how our brain is wired, okay? That's the simplest thing to ask. Where it turns out that the wiring of our brain is outrageously complicated. We have 10 to the 11, or how is that, 100 billion neurons in our brains, each of which has 1,000 connections. Okay? That's an awful lot of connections. And that basically is self-assembly. And so one of the biggest problems in neuroscience is how does this neuron 1053, find with neuron 6,553,221 to make a connection. And they often travel very large, the axons, which grow out from the central part of the body, often travel huge distances, up to 50,000 times the size of the core cell, to find a partner to make a mate with. Okay? So we're developing tools in our laboratory to try to help neurobiologists understand these questions of neuronal guidance. The key actor in the experiments that we do and in wiring up the brain is something called the growth cone. The growth cone is the end of the axon. It's basically the sensory and motility organ of the neuron. It snips its way through your brain and crawls its way through the brain. It generates the force to find another object. And the machinery of the neuron is absolutely amazing. Of the growth cone is absolutely amazing. So if you will, we'd like to, if someone could dim the lights, that would be great, because this is a really beautiful movie that I don't think is getting justice made to it. So So this is a growth cone under DIC, and was described how DIC works. It was described beautifully this morning. It basically allows you to see subtle phase differences. So this growth cone is a very, very thin object that crawls on a surface. This is the leading edge of the neuron, and you can see there's all sorts of interesting mechanics happening up here. With modern biochemistry, we can create versions of the relevant proteins that are fluorescent, or inject things that bind to the relevant proteins that fluoresce to visualize the kinematics and the dynamics of what's happening inside of the cell as it crawls. And in this movie, you can see where we've made the actin in the cell. The actin is a molecule I mentioned earlier. It works with myosin to contract our muscles. But actin and myosin also work together in a crawling cell to pull the cell forward. So this, if you look here, you see there's a net outward flow of actin from the outside in. But if you also watch carefully, the cell is actually moving forward. So the cell is actually has a net flow inside backward, even though the net motion of the leading edge is in the opposite direction. Interesting conundrum, but it makes sense, and I don't have time to explain it. The key thing is that this thing is constantly generating forces. I guess I'll explain it. It's constantly generating forces. It's like the engine of your car that's spinning around in circles. If you want the car to move, you make a physical connection between the engine and the wheels, and then the wheels start to rotate. There's always force being generated to pull this actin back, but if that actin sticks to the substrate, it doesn't move backwards anymore, and it pulls the cell forward. That's the basic idea. So one of the things we're trying to understand is when a cell turns, how the cell signals itself to go in one direction to the other, and how it generates force. So a type of experiment we're doing is we're taking beads that are being trapped with optical tweezers, and these beads are coated with a substance that cells recognize as adhesion sites. And it's called big dermagglutinin. And here you can see the edge of the growth cone here, the large flat region, and each of these beads is initially in an optical trap. And you can see the beads have some really interesting dynamics. They don't just sit there, they're jiggling back and forth a little bit, and eventually they get pulled out of the optical traps because they get bound strongly to the engine of the cell motion. The clutch engages and eventually pulls them away from the cell. So experiments like this allow us to probe the mechanisms by which the clutch inside of the cell works. And so by precisely calibrating our optical traps and carefully analyzing these movies, one can create data records that look like this. So each of these lines represents the force that was felt by a single bead attached to the cell surface as a function of time. And we've measured the force at 5 different spots in the cell. And you can see there's a great diversity of things. Every particle is feeling something a little bit different. There doesn't seem to be strong correlations in the forces. Though the traces have very similar shapes. An interesting feature of these traces is brought out if I draw a bunch of parallel lines that are canted a little bit, that these aren't just normal fluctuations that are going back and forth in the center. What you see is occasionally a bead that's just fluctuating near the center of the trap gets pulled at a constant rate away from the center of the trap and then snaps back. And typically when it gets pulled away from the trap, it always gets pulled at a constant rate and then snaps back. It's an interesting observation. It suggests that the beads are being intermittently coupled and decoupled from the cytoskeleton as it's being trapped in the optical tweezers. And right now, today, we're analyzing these traces and doing biological manipulations to understand the mechanics of how the cell generates these tens of piconewtons at force and understanding the mechanism. Ultimately, to try to understand how the cell can figure out where to go inside your brain. Okay? So that's one example of how to use optical traps in an experiment. So the other example I wanted to talk about was measuring much smaller forces Not in biological systems that are really complicated and dirty, but really simple, controlled physical systems, okay? So I'm particularly interested in colloidal physics, and femtonewton forces are pretty important in that range. And let me just tell you a little bit about colloidal materials. So colloidal materials have been used forever. As long as there's been technology, there's been colloidal materials in engineering. It's been around with all sorts of coatings and pigments like paint and ceramics and personal care products. And recently, more sophisticated, smarter colloids have come around. Things like pregnancy tests involve controlled aggregation of colloidal particles through biologically mediated binding between particles. And also, when colloidal particles have crystalline order, they can interact with light and selectively reflect the light, just like liquid crystals, and there are all sorts of interesting potential applications of photonics that one can think about. But in all of these cases, the properties of the colloidal material ultimately are determined by the microscopic structure of the particles and their interactions. And this is where forces come in. Because if I can understand and control the interparticle forces, I can understand and control the structure and therefore manipulate the properties of the material. And here are some very simple examples. If I have a low density of particles that are not really interacting unless they touch each other, then their structure is basically random. There are very weak correlations in the structure and the dynamics of the particles. But if we crank up the interactions so that they're strongly repulsive, either by giving them long-range electrostatic interactions or by just increasing the volume fraction so they feel each other's hard cores more, then the structure becomes highly correlated. You can undergo a first-order phase transition and make a crystal, something with a long-range order which has interesting optical properties. Okay, so the structure and the properties of these materials depend on the interactions, and therefore I want to measure them. Okay, so it turns out that measuring interactions between colloidal particles, especially at long range, is hard because the forces are weak. Okay, so if you look at the sorts of things people use to measure small forces, there are things like the surface forces apparatus, which measures micronewton forces between macroscopic surfaces. And then there's the fabulous AFM, which is very happy in the nanonewton range. You can push it down to piconewtons if you work hard. And then also the optical tweezers, which is very happy in the piconewton scale. And all of these cases, whenever you do a classical force measurement, like the one I showed you, where you have some sort of calibrated spring, and by looking at the displacement of the spring, figuring out the force between the interfaces, you always have to deal with issues of how do I calibrate my spring. In the surface forces apparatus, it's actually a spring. In the AFM, it's a cantilever. In the optical trap, it's the gradient forces. And then you always have to worry about perturbations from the transducer. And all these things become more and more important as you try to measure smaller and smaller forces. And they become especially difficult if you want to measure femtonewton forces that are important for colloidal physics, because not only do you have to deal with these things, you also have to contend with thermal fluctuations. Thermal fluctuations become exceedingly important. So you may have noticed in the movie I showed earlier in the weakly correlated system that these particles were undergoing a little random dance. That random dance has been known about for about 170 years now. It's called Brownian motion. And I wish I could whip my movie, but just watch it a few times, and you'll see the key thing that this Brownian motion comes from thermal fluctuations, basically. And on average, if there's no forces applied to the particles, they don't go anywhere, but they do sort of sample a range. They have a mean square displacement that increases linearly with time. This data is from analyzing this movie. So typically what you see is that the mean square displacement increases linearly with time with a slope which we call the diffusion coefficient. Okay, so if you're trying to measure forces between two things and with some force transducer on top of the displacements that you would see just due to the forces you're interested in, you would also see all the thermal fluctuations, and you have to learn how to average those out. So we want to measure a really small force on an object in the presence of thermal fluctuations. How do you do it? So let's do a little thought experiment where imagine that we have some particle in a fluid and we apply a force to it. And we're going to say that force is 100 femtonewtons. And we're going to put in the right values for the diffusion coefficient and the velocity due to that force. And what you would typically see if you looked at a single trace of an experiment of displacement versus time, all three of these traces have the same force on the particle, but you can see they have very different dynamics. In fact, the force is trying to push them up, but occasionally there's a finite probability that they'll even go in the opposite direction. So you have to come up with ways of dealing with the statistics. We have to take a statistical measure of what's going on. So what you have to do is you have to look not at the instantaneous velocity, but at the average velocity of the system, which is going to be proportional to the force with some prefactor called a hydrodynamic mobility in front. And then also, you can measure in that experiment all these fluctuations by looking at the mean squared displacement. You can measure this diffusion coefficient. Okay, so thanks to Einstein, we know that these two things are related. This diffusion coefficient and this hydrodynamic mobility are very intimately related. It's one of the first, I think, the first example of a fluctuation-dissipation relationship. Einstein told us that this D is just related to this B. So our simple idea for measuring these experiments is, well, why don't we just take a system that's being forced, take lots of statistics, measure the average velocity, measure the diffusion coefficient. If you measure the velocity and the diffusion coefficient and use Einstein's relationship, then you can basically cancel out what is typically, what can generally be an unknown mobility factor to calculate the force just by looking at the drift and the diffusion of the object. So typically the force is proportional to kT times the velocity divided by the diffusion coefficient. So the characteristic energy scale is kT. V over D gives you a characteristic length scale. And length scale and energy scale come together to give you a force. So it's a very simple idea. The problem is that we want to measure forces in particular configurations. We want to know the force between two particles at a certain separation, and it's hard to get good statistics in a configuration like this. I want to know the force between these two particles at this separation. With a single trace, I can't do it. And this is where the optical tweezers come in. We don't use the optical tweezers as force transducers, but we use them to set up initial conditions. We bring the two the particles next to each other with optical tweezers. We let go, and then we look at how the particles fluctuate near each other. The reason we link the traps is so that we can get good statistics and control geometries. And the third nice fact is that when we actually record the data, the laser is off, and we don't have to worry about any perturbations due to laser light. And so the way we analyze the data, we have all these fluctuations. And so what we do is we look at the probability that the separation between the particles will change by a certain amount after a certain time interval. And these are a bunch of histograms showing that distribution. The green distribution is the distribution at the shortest time interval. You can see that it looks pretty Gaussian, except it's shifted a little bit to the right from delta R equals 0. And at longer and longer time lags, you can see that Gaussian distribution gets fatter and drifts significantly to the right. Okay. Since these distributions are Gaussian, we can fit them with only two free parameters, the center of the Gaussian and the width of the Gaussian. We plot those things up as a function of time, and lo and behold, we have what we want. We get our average drift velocity, which is just the slope of the center of the distribution as a function of time. And we get our diffusion coefficient, which is just half the slope of the width of the distribution as a function of time. So in a single measurement, in a single configuration, we can measure both the velocity and the diffusion coefficient. And we just do what we said we did. We just take the velocity we measure divided by the diffusion coefficient we measure, and we get a force distribution. So here is, for two spheres that are interacting with each other, the drift velocity in nanometers per millisecond as a function of their separation in microns. You can see as they get close to each other, they drift apart more. Here's the diffusion coefficient as a function of separation. As they get closer, they don't fluctuate as much. And when you take the ratio of these two, you get the force between the particles as a function of their separation. And the force scales are on the femtonewton scale, and we get error bars on the order of femtonewtons. A femtonewton is a very small force, and the best calibration for a femtonewton that I've come up with is that if you extend your left hand as far as you can, and then extend your right hand in the opposite direction, a femtonewton is the gravitational attraction between your thumbs. You could never measure that femtonewton because the magnets of my thumbs are too big and there are lots of much bigger forces around. But if you're a poor little particle with nothing else bothering you, then a femtonewton can make a big difference. Okay, so it's a very simple point here is that just by looking at the kinematics, all the dynamics comes out of the temperature. And we can calibrate things with a thermometer. So what do we use this for in our lab? One of the things we use it for is to understand the electrostatic interactions of colloidal particles, and I don't have time to tell you about how any of that works. But I'm just going to show you some example data. So, in particular, we're interested in a system of polymer particles suspended in oil as we add different quantities of additive to the particle. And if we add no additive to the material, we see a very weak repulsion that's close to the noise level. And as we add our mysterious additive to the material, you can see an evolution of the interactions between the particles, okay? And in particular, it turns out what this additive is the surfactant. What it does is it charges the surface of the particles. Here's the charge on the surface of the particles. And it also puts some charge in solutions, which creates some screening. And here's a measurement of the ionic strength as a function of the concentration. So by measuring these forces, we can start understanding what's happening on the surfaces of these particles as we modify solvent conditions. Okay, so I want to spend the last couple of minutes telling you about an extension of this technique, which is pretty interesting and ties back into the motivation for understanding interactions between particles. And I motivated understanding forces between particles by saying we want to control materials. Materials, if you have certain interactions between particles, those interactions determine the structure. One of the key assumptions that people make when they're building up a model, in most cases, is that the force on any one particle is a sum of all the forces between that particle and all the other particles. It's called pairwise additivity. Okay, it's assumed all over the place, and there's no reason to believe, especially in electrostatics, in the ranges where people assume it, that it should be true. And we're trying to test that. And so what we do is we take not just two particles and put them together, but we bring a bunch of particles together. In the simplest case, we bring three. It makes our data analysis a little bit trickier because what was once a one-dimensional relationship between scalar transport coefficients, velocity, and diffusion, we now have a multi-dimensional relationship. But it's still a linear relationship between a tensorial diffusion coefficient and a vectorial velocity. But both of those tensors are directly measurable by analyzing movies of particles fluctuating when they're next to each other. And here's a definition of that, but we don't have time. The key point is it's the same idea. We measure velocities, we measure diffusion coefficients. I don't have time to explain this, but the key point is that we can measure the diffusion tensor now from real data. And we also measure velocity from real data. And so we can take particles under identical solvent conditions, and we can measure the forces between them when there are two, when there are three, and when there are seven, and see if they add up. And so here's an example. Under certain solvent conditions, we took two particles, and we found a force versus separation that looked like this. Okay? We fit it to a theory for electrostatic interactions that told us there was a certain amount of charge on the surface of the particle and in solution. We said, okay, there's this much charge on the surface and on the solution. Let's bring a third particle in and measure the forces on the expansion mode of the particles. And we found that if we just added up the red curve here is actually just the sum of the forces from the fit of the two particle forces that we measured earlier. And it seems that the pairwise additivity works great when we go from 2 to 3 particles. But we're not quite doing condensed matter physics yet. We need a billion or so to get phases. And then we start seeing interesting things when we have more particles. Here we have 7 particles. And we find that the prediction that we make from adding up the pair interactions significantly overestimates the forces that the particles actually feel. This is for one set of solvent conditions. Turns out for different solvent conditions that effect is an even more dramatic effect. In a situation where there are fewer ions in solution, we can find pretty good pairwise additivity. At the 3 level, we start to see deviations, but we can see very significant extreme departures from pairwise additivity, which we're not even sure if we believe yet. because they're so extreme. But we definitely see some sort of departure from pairwise additivity, and what we're working on now in our lab is trying to understand what sorts of solving conditions and what are the physical mechanisms by which electrostatic interactions between particles no longer add up as you would expect them to. So that was sort of a whirlwind tour of what optical tweezers can do, and some different types of very different examples of how you can use them to do science. First example was very purely biological, trying to understand how cells move with a piconewton scale force, and there a simple force measurement where you just relate displacement to force works great. But we also use optical tweezers to measure much smaller forces in thermal systems and to do basic physics experiments. So I just want to point out a couple of things. Most of the work I told from my own laboratory that I talked about today was done by Sunil. Sunil and Jason did the physics types experiments, and Sil did the cell type experiments. I just want to point out here, there's a big question mark next to postdocs in my lab. I have 2 postdoctoral positions open in my laboratory, so if you're graduating and you're looking for a job, come talk to me. All right? So, and I hope you'll talk to me now by asking me questions.
Okay, we've got lots of time for questions, so let's start up there.
This is probably a stupid question. Do you have any trouble with local heating if you're driving 100 milliwatts kind of microns?
Sure. Okay. So that is not at all a stupid question, and we have to work very hard to make sure that we don't have local heating. And so we have a couple of different setups in our laboratory that are designed to get around certain issues. So the key point is that there's a heck of a lot of laser light there, and if there's any absorption line, you're dumping a lot of energy in. Okay, so the best way to avoid heating is by choosing your wavelength very carefully. You can't trap everything, and you can't trap everything in any wavelength. So for our systems and organic solvents, we use visible light. For biological systems, we use infrared light, and we do measurements as a function of laser power to make sure that we don't see differences as a function of laser power. The key thing that's really nice about heat transfer, though, at these length scales, is that heat transfer is done by conduction. Conduction is basically a diffusive effect, where the phonons are diffusing away from the source of heat. The energy diffuses away. And diffusion is amazingly fast at short length scale and terrible on length scales like you described earlier today, right? So it turns out that if you heat up a 1 micron colloidal particle in an organic solvent by a degree, it basically back at the equilibrium temperature within less than a millisecond. I believe it's 100 microseconds. I don't remember the exact number. So heat transfer by diffusion helps a lot. But it's really important, though, that you avoid heating in the first place so you don't get weird chemical things.
More questions?
So you briefly showed that the force that is feeling is a function of its refractive index. What's the wavelength dependence of force?
Yeah, so it basically comes, so the key, okay, so I didn't get into too much detail. The way I described it is I said that the force was proportional to the index. But typically you have different materials competing to be in the focus. So if I have a glass particle in water, both the water and the glass particle want to be in the focus. So what's really important is the index of refraction mismatch that determines who's going to win. Okay, and the specific value of the index of refraction at the operating wavelength for both of those materials matters, right? So you need to make sure that at the wavelength of your laser operation, not only are you not heating up anything, but you also are working where the index of refraction mismatch is a favorable.
Question back there?
Yeah. I found this assembly routine just really fascinating where you just had to capture 20 particles. Could you give me an example of how that might be useful or marketable in biology?
Yeah, okay, so for this stuff, so actually I didn't get a chance to show you in the talk, so I'm going to show you a movie that is not the best quality, but might answer your question. But I don't have it in this talk, so I'll just wipe my hands. So, okay, so cells have control systems, right? They have a homeostasis. They try to maintain a certain set of things, variables, right? So a great way to try to understand how the cell's control system works is by opposing it with a control system that you're operating. So in that experiment where I showed, in the experiment with the cell where I showed the beads that were attached to the cell membrane twittering around and then getting pulled out, right now in our laboratory we're developing a modification of that experiment where we move the optical traps and adjust the laser power to try to keep the bead in the same spot. And by looking at how the cell, by pairing one control system against the other, we can try to understand the control systems that the cells are developing. So the thing where I was assembling stuff is one simple example of a control loop that's a controlled position loop. We have all these things here, we move the traps around so they end up here. We're doing the same thing, except now we're saying keep the particles here no matter what the cell does. And by recording what you have to do to keep them there, you know what the cell's doing. Does that make sense? So that's the example we're pursuing pretty actively.
More questions? Oh, yeah.
For your femtonanometer measurement, do you have to worry about flow, or if you do like control?
So okay, so there's so it depends on what exactly you're talking about. So if you're just talking about a two-particle measurement, and those two particles are far away from any walls, so they don't have any hydrodynamic interactions with anything except themselves. If there's a little bit of drift in the sample, it's not going to affect the force measurement because we're really interested, the relative velocity of the particles tells not the absolute velocity, tells you the force between the particles. But you can get into very serious trouble, extremely serious trouble, if you take particles and you put them next to a wall and there's a flow. Things that should be repulsive can end up being attractive, and lots of very weird things can happen. So, in principle, so I should say one thing is that the technique that we developed accounts for the flow that's created as one particle moves. So it describes, it deals with, in fact, it measures the hydrodynamic coupling between two particles. It does not tell you about what other things outside are doing. So if you construct your geometry right, so only those two particles matter, our technique works. But if you do it next to a wall or you have an external flow imposed, under certain set of conditions it can be completely destructive. And you have to be a little bit careful about that.
Yeah.
How do you silicon particles and the DNA and the RNA strings?
Sorry?
How do the silicon particles and the DNA or RNA strings, how do you connect them?
How are they connected? Okay, so that wasn't my experiment, but I can tell you that there is a whole toolbox of ways to attach molecules to beads that's really exploded in the last 20 years. And the most common thing for people to do is to take a protein or nucleic acid and attach a short sequence to it called biotin. And then you can buy a surface that's coated with the thing it likes to bind to called striptavidin, and you just mix it up and they stick. But there are lots of different chemistries that you can use, and you always have to be very careful about which chemistry you use. But the people that sell beads often have a lot of information about different protocols that you can use to attach molecules to surfaces.
What else?
Can I ask you one?
Yeah, sure.
So you guys say there's a linear effect. Is there any way to do a two photon event where you're actually exploiting a hyperpolarized movie instead of a linear polarized?
Okay, great. So maybe. So I guess now I understand what your first question was really about. Okay. So I wasn't taking it for advantage. Well, maybe, I'm not sure. So one issue, I'll tell you a little story. Okay. So it's really hard to trap small things. And lots of people are really interested in coming up with better ways of cranking up the forces. And people have looked at lots of different mechanisms. One mechanism is to look at, to exploit dispersion, very strong wavelength dependence. And some people believe that if you if you have a material that has a resonance at a particular frequency, whether or not it's a 1 photon or a 2 photon process probably doesn't really matter very much. I'm not sure, I'm guessing. But the idea is if you detune your laser relative to that resonance, you might be able to jack up the optical forces. This is an area that's very active research. I'm not involved in it, but it's a very important area because cells are relatively strong, and they really put a lot of the forces that cells generate are sort of like where the AFM peters out. Too low for the AFM, but too high for optical tweezers. And you can make your AFM a little bit floppier so you can measure low forces, but you can still only measure it at one point. And that doesn't tell you that much information, because you can see when I did at 5 points, I got very different answers. So if you really want to understand how a cell works, it would be really nice. It's nice to measure it at lots of forces, at lots of points, and it would be great if we could generate lots of forces. And if you have ideas about how to do it, I'd love to talk to you about how to crank up those forces. But I've heard people talk about, dispersive effects and potentially 2 photon effects.
You're looking for optical vice grip. You're looking for optical vice grip.
Yeah, exactly. Yeah, exactly. We really want to nail that sucker.
Okay, all right.
You mentioned that you have to worry about your particles being close to walls.
Yes.
How far, when you make these samples out, how far away do you have to be before you have the samples?
Yeah, great. So I'll give you 2 answers to that. I'll give you the experimentalist answer, right? You do it at one value, the distance away from the walls, and then you do it at a different value and you see if the answer changes, right? That's the tried and true way of doing things in experiment. But theoretically, if you were to read up a little bit about hydrodynamics at low Reynolds numbers, you find that if the particles are farther away from the wall than they are from each other, then you're in good shape. So that's a pretty, so the separation between the particles is much closer than the separation from the wall, and the particles are much farther away from the wall than their diameter, you're also in good shape. And those are some good rules of thumb.
All right, I'm going to take advantage and ask one question about the beads in the sea slug neuron experiment.
Yeah.
You drew all these slanty lines.
Yeah.
So that you got a characteristic velocity of motion.
Yes.
Is that just the myosin actin sort of velocity that you're measuring there, or is there other information contained in that?
Great. So I plotted things up here as force versus time, but I also have plots where I do distance versus time. And when we plot it up as distance versus time, the velocity that we get is almost identical to the backwards drift velocity that we see in this movie on the left. So it suggests that the system goes from not being bound at all to the cytoskeleton movement to being very tightly bound. But it's not, there is significant variability from cell to cell on what those velocities are. So the experiment that we're gearing up to do now, and still probably a couple of years away though, is to be able to make a movie like this while simultaneously getting those first curves, and we can measure how much slip there is between the bead and the cytoplasm, and then we can get more detail about exactly how that clutch works and what its properties are.
All right, I think we better stop here, and we're going to take a short coffee break, and we'll resume in 10 minutes.